Okay, so we're going to have a look today at catalysts, and first of all we're going to have a look at heterogeneous catalysts. Now, an example of a heterogeneous catalyst is the use of iron in the production of ammonia using the Haber process. The reason this is considered to be a heterogeneous catalyst is we have nitrogen and hydrogen, which are reactants, are in the gaseous phase, and then iron is a solid, so that's in a different phase. Now, the way heterogeneous catalysts tend to be used is on what's called a support medium. So a support medium could be something like a wire mesh that's made of iron, and then we pass our gaseous reactants over it. That's used to significantly increase the surface area. We can also use things like ceramics. So we can either use wire meshes, or we could use ceramics. It's incredibly difficult to draw, so I'm going to send you a link in this video to some pages where you can actually have a look at these, because if I try and draw them, it won't go very well. So the key thing about heterogeneous catalysts here is that the reactant and the catalyst are in a different phase. Now, the way heterogeneous catalysts work is in a four-step process, really. So we have our catalyst surface here, and then our reactants adsorb to the catalyst surface. Now, that word adsorb means basically to stick to. So the reactants adsorb to the catalyst surface. That's step one. In step two, the bonds between the adsorbed reactants weaken. So this process of the molecules sticking to the catalyst surface causes those bonds to weaken. In step three, a reaction takes place. Obviously, I haven't drawn enough. I'll do this here actually now. So I'll draw an extra hydrogen in here. Obviously, we'd actually have more molecules sticking to each other. But basically, the reaction takes place. So the weakened bonds mean that a reaction can take place. And then in our final step, the products deadsorb and move away. So the four steps: reactants adsorb or stick to the surface. That's adsorb, not absorb. Adsorb to the surface. That causes the bonds in them to weaken. In step three, the reaction occurs and new bonds are formed. In step four, the products deadsorb and move away. There is a problem with these though, because we can get something called catalyst poisoning over time. So in catalyst poisoning, we can get other substances can stick permanently to the catalyst surface. Now, in the case of the Haber process, some of those things that actually stick to it are carbon atoms, and that comes because through some of the small amounts of impurities as a result of the hydrogen production that's used to it. In a car catalytic converter is a heterogeneous catalyst. We can get, again, small amounts of carbon as a result of unreacted hydrocarbons, and we can also get impurities in the fuel poisoning the catalyst, sticking to the surface, and this stops or prevents access to the reaction site. Okay, So we've dealt with a heterogeneous catalyst. Should have mentioned earlier on actually that the word heterogeneous, if we just have a look at the word heterogeneous here, heteros is the Greek prefix for meaning different, and genus means phase or state. So we're talking about the reactants and the catalyst being in different phases. So there is a specific example that we need to understand, and it highlights really how transition metals can act as catalysts. And that's the reaction between sulfur dioxide and oxygen to make sulfur trioxide. So all of these reactants are in the gaseous phase. This is one of the most important reactions in all of industrial chemistry because it produces sulfur trioxide, and when sulfur trioxide is dissolved in water, it makes sulfuric acid, which is one of the most important or the most important inorganic acid we use. Now, this reaction will not take place at room temperature. You cannot heat sulfur dioxide and oxygen together and get sulfur trioxide. We need vanadium 5 oxide, V2O5, in order to carry that out. And there's a two-step process that this occurs in. The first stage is that our catalyst, V2O5, reacts with sulfur dioxide to produce V2O4 and sulfur trioxide. If we were going to put state symbols in here, we'd think about these being solid and these being gaseous. So these are heterogeneous catalysts. In the second step, V2O4 reacts with half an oxygen molecule to make V2O5. Okay, so it's a two-step process. Now, if we want to combine these two equations, we simply add all of the reactants in both steps together. And all of the products together. And then we can cancel out anything that appears the same on both sides. So that and that cancel, and that cancel, and we're left with our overall equation for the reaction. SO2 plus a half 2 goes to SO3. So we can tell that the vanadium oxide is acting as a catalyst in this because it's a reactant in step 1 and a product in the final step, step 2 in this case. And it's although it's involved in the reaction, it's unchanged overall. So this is an example of a transition metal being able to act as a catalyst because of its ability to have variable oxidation states. Okay, so let's have a look at now homogeneous catalysts. So homogeneous catalysts are catalysts where the reactants and the catalysts are in the same phase. So the reaction we're going to have a look is the peroxide disulfate reaction, which is S2O8 reaction with iodide ions to produce sulfate ions and iodine. Now, this reaction has a very high activation energy, and the reason it has a high activation energy is because we have a negatively charged peroxide disulfate ion and negatively charged iodide ions. So these ions are going to repel each other when they approach each other, which means that the reaction happens very slowly because the chance of a collision between these molecules occurring spontaneously is low because of the repulsion between them. So there is a catalyst for this. And again, it's a two-step catalyst process. That catalyst is iron 2 ions. So S2O8 minus, so the peroxide disulfate ion, reacts with 2 Fe2 plus ions. That produces our 2 sulfate ions and also produces 2 Fe3 plus ions. So we can see what's happened here is that the ion, again, is the last example, has been able to temporarily change its oxidation state in order for the reaction to take place. So this is another example of a transition metal ion being able to change its oxidation state. Now in the second step, our Fe3 plus ions, two Fe3 plus ions, react with two iodide ions to make iodine and two Fe2 plus ions. So as we can see, this happened last time. Fe2 plus was a reactant in step 1, and it's a product in step 2. So overall, it's unchanged. If we were to do what we did last time, which was combine these two equations, so let me that slightly so you can see all of it. Then what we can see overall is that we can cancel that and that out and that out, and we're left with our overall equation for the reaction again. So that and that produces that and that. So again, the Fe2 plus is able to act as a catalyst again because of the variable oxidation state. It should also be mentioned that it is providing an alternative reaction pathway with a lower activation energy. So that's something that we'll think about quickly in a moment. Interestingly, this reaction will happen exactly the same if we react it with Fe3 plus ions instead of Fe2 plus ions, in which case this is the first step that takes place and this is the second step that takes place, and we still end up with exactly the same process. So in fact, you can a catalyst that works for this reaction is either aqueous Fe2 plus ions or aqueous Fe3 plus ions. And something I should have said earlier on, just to be clear, is that all of these are aqueous. So this is a homogeneous, homos meaning the same, so the same phase. Just as I said earlier, we do need to remember that what's actually happening in one of these reactions, if we think about an energy profile for this reaction, so the reaction we've spoken about will occur at room temperature, but the activation energy is very, very large indeed. So activation energy there. The catalyst is providing an alternative reaction pathway with a lower activation energy. Thank you very much.